Hi folks, well I'm back. So continuing on with the previous problem here. So we've gotten this far. T equals the integral from 0 to 1000 of dx over square root 150x minus 0.025x squared. And this thing's probably integratable. I'm thinking a trigonometric substitution. Generally speaking, I usually recommend this. If something kind of looks like Pythagorean theorem, a trig sub probably will work. However, I'm going to go ahead and integrate this numerically. So this basically, now think of it like this. This is the integral 0 to 1000 of some function times dx, where the function that we're looking at is 1 over square root 150x minus 0.025x squared. Now, before we move on, there's some things to observe about this function. For starters, this function has a vertical asymptote at x equals 0. So this function is not defined at x equals 0 because we'd have a 0 in the bottom here. That doesn't necessarily mean that we can't integrate right up to x equals 0 and get a finite value for the area under the curve. That's kind of a Calc 2 topic. I'm going to go ahead and assume that we will get a value here and start talking about the setup and how to do it. And we'll know from our numerical solution if there's some sort of problem. So here's a picture. Oops, actually let me go back and just kind of talk about this function. Not 100% sure what it looks like, but we do know it has the asymptote at x equals 0. The idea behind numerical integration now, remember what we're trying to do here is we're going to break this into rectangles, and each rectangle is going to have a length equal to the function value times the width dx. So how you break these into rectangles is very important. So I'm just going to draw a couple of them. All right, 1, 2, 3. That's probably enough. One more. Well, oops. Maybe one more. Maybe something like this. Now, if you look at my rectangles, there's different ways to draw them. I usually draw them so that when I'm working on numerical analysis, that the function goes right through the midpoint of the rectangle. And the reason for that is when you're doing the area calculation, you notice that you get kind of an underestimate here, overestimate here. Now, when you look at that very first rectangle, pay attention, since we know there's an asymptote here. Notice that just by observation here, I can see that this area that I'm missing is definitely less than this little overestimate right here. So my guess is what's going to happen when we integrate this function is that our answer, I think, is going to probably come in a little on the low side. And again, I'll show you how you kind of handle that in Excel here in a few minutes. Now, the idea now is that in Excel, I need to be able to generate different x values and different function values. So I'm just going to get right to it. I'm going to call this the first rectangle, this the second, third, fourth, fifth, etc., etc. In general here, we have I rectangles. So in my work here, I is going to take on these values, 1, 2, 3, down to some number. I'm just going to say n. Now, I'm going to get right to the nitty-gritty here. I've already worked this, and I know I've got to use a pretty good number of rectangles to do this, so I'm going to use n equals 50. I think I used 50 to get 2 sig fig accuracy here. Looking at the work, we're going to need actually this x value right there, x1, and then we're going to need this x value, x2. We need those to calculate the function value. See, we're going to need that length to get the area of that rectangle. So, looking at this other rectangle here, we're going to need this length to get the area of this rectangle and so forth. So, in general here, I'll just write down the answer and talk about why. I'm going to define what I'm going to call an x sub I. And it's equal to I times delta x minus 0.5 times delta x. Now, I suppose we should probably talk about the delta x. Delta x is the width of each rectangle. We can get that if we take the upper bound minus the lower bound divided by n. A and b are kind of generic calculus terms for lower and upper bound. So in this example, the delta x is equal to 1000 minus 0 over 50. Okay. Now I'm going to leave it like this, and I'll show you how I kind of program this stuff into Excel. The reason it's I times delta x, well, if you take a look at this rectangle, 1 delta x would put you right to here. But I don't want to be right here. I need to be at the center of this rectangle. So if I subtract half a delta x, that puts me right there. Let me check the second one. 2 delta x would put you to here. come back, half of a delta x would put you right here. In general, I times delta x will put you at the right-hand side of any rectangle. And then if we subtract or come back left, half of a delta x, that'll put us at the center of the rectangle. So what I'm going to do over on the right is I'm going to make myself a little column and have Excel calculate all these values for me. I'm going to do that in a moment. Next thing I'm going to do is I'm going to have it calculate function values for x sub i's, where I'm going to use this for my function, and I'm going to have Excel calculate all of those. Then what I'm going to do is I'm going to calculate what I'm going to call an a sub I. And what that's going to be is it's going to be the area of each rectangle. And if you look at this rectangle, like this first one, if I take that, which is the function value, times delta x, I'll get the area. So what I'll do is I'll have that in Excel. I'll have it calculate a number, do all of them. And then in the end somewhere, we're going to have to add these all up. So I'm going to go ahead now and kind of change my computer screen a little bit. This might make a little sound. What I'm doing is I'm shifting this around now so I can get at the keyboard. Alright, so that I can start doing these calculations here. Alright, so now I can move my little mouse around here. I'm going to bring my Excel forward here a little bit and maybe move it over here. I need a little room. Alright, so just like I mentioned before, we have a lower bound. I'm going to call that A. I'm going to make another column, up B for the upper bound. Okay. N is going to be the total number of rectangles, and the very first thing I'm going to calculate is delta x. I'm just going to call it delta x. So I'm going to go ahead and put in these values. 0 for my lower bound, 1,000 for my upper bound. I'm going to go ahead and use 50 rectangles. I know I need to use at least 50 to get close to 2 sig fig accuracy in this example. I'm sure it's because of this asymptote here that's giving me a little bit of trouble. All right, delta x equals. Now in Excel, when you hit equals, what it does is it tells you there's a formula coming up. And I'm going to use parentheses here, and I want this to be b minus a over n. Now the cool thing is, the way I set this up, whoops, this thing didn't do my deal here, right? I need a divide by n. Whoops. Divide by n. Oops, sorry, this did not like what I did here. I gotta go back. I'm gonna kind of start this over. Alright, del x equals b minus a. Now notice though that I'm clicking in the cells rather than typing a and b. Now I need this to divide. Whoops, it's not liking that divide. What's going on here? Question mark. Oh, there we go. Okay, I was hitting shift. Now I want it to divide by n, by that cell right there. I'm going to hit enter. There's my delta x. Now by setting it up like this, notice I could go back if I wanted to, and I could actually hold on for just a moment here. Sorry about that, I'm back. Had to answer the phone. I know I got another interruption coming again here, but I want to make sure and get this as far as I can. So I can go back and I can update my value of n here. You know, maybe I could put it to 100. And again, notice it automatically updates my delta x. That's a real nice feature of setting it up the way we're setting it up. All right, so I'm going to come over here and I'm going to generate my i's. And I like to label them column-wise. I'm going to come down here. I is equal to 1, 2, 3. Now, Excel's really good about patterns. I've showed it a pattern. Now I'm going to take this and drag it down to 50. Oops. All right, boom. Then I'm going to have my x sub i's, and I usually would just call that something like x sub I. I usually know what that means when I type it. Equals I times delta x. Now that's got to be double dollared. Hit F4. If you've ever heard me talk about my numerical stuff here, F4 locks that thing down. So I times delta x minus 0.5 times delta x. That again has to be locked down, so F4 it. That double dollar means that when we scroll, Excel will not allow that cell to scroll with it. I'm going to fill these all out. If I did this right, this one should be just short of 1,000. Boom, 990. So our delta x is 20. It's 990 because that's right. Remember, we centered the rectangles. All right, now I'm going to have it compute f of x sub I. And here's where I'm getting that from. This is this function right here. So that's going to equal 1 divide by, good spot for parentheses. Let's see. 150 times x, and I'm going to get x from right here, minus, just 1 second, I'm going to pause this. All right, sorry about this, folks. I had to answer the door there, so I got to kind of figure out where I am here. Let's see. We were calculating the area. I was in the middle putting this function in here. All right, so 150x minus 0.025x squared. All right, 0.025. Then I need a times x. I'm going to go ahead and click here. X needs to be squared. I'm going to close the parentheses. And then square root outside the parenthesis. That should give us the radical part here, square root of. There's our functions. So I'm going to go ahead and drag this down, get values for that function down to 50. Okay, boom. All right, and then a sub I, because remember what we're trying to do. Oops, get that out of there. What we're trying to do, f of x dx is an area. We're trying to calculate the area of all these little rectangles here. So we need to take the function value, right, times the delta x. So a sub I equals the function value. Just go ahead and click right here. Multiplied by the delta x. Now, because delta x is up here, we don't want that to scroll down. In Excel, we're going to want to double dollar that. I'm going to go ahead and drag, get all 50 of these. There we go. And now, dun, da, 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 the end of this thing. All right, so our total time, t equals, now if I put the equals after t, it's just typing in equals. Then I'm going to come over here and actually hit equals in the cell. That's going to give it a formula. We want the sum of all these little areas. And I'll go up and see how we did. 5.1. I think when I looked this up, it said 5.2 or 5.3. So let me talk a little bit about error and what's happening here. So the first time I ran this with 10 points, I think I came in around 4.6, 4.7. And knowing that I had a little problem here, this thing, remember, I think it's asymptotic here. So I think there's area missing here that's my function's not getting, real well. So I increased the value of n to 50, or I think I increased it to like 20, and I got to about 4.9, and then I increased it to 30 or 40, and it went to something like 4.95, and then I went to 100 points, and I got 5.0, basically 5.1. Now I've looked at the answer to this; it's 5.2 or maybe 5.25 or something. So I'm close enough that I'm happy that this is done correctly. Here's a few things here. If I was interested in getting more error or a better result, I could do. We could keep increasing this value of n. If I run this to 100, then I would come down here. Actually, we'll go ahead and do that. 100. I'll show you what it looks like. Now keep in mind we're at 5.09. Now if I increase that to 100, we now have to increase all of these to 100. All right, so I'm going to do that. Here's my pattern. I'm going to take that down to 100. Excel's really nice. It kind of tells you where you're at. 83. Oops, a little too high. This might be a little bit of pain. All right, there we go. 102, 101. Okay, 100 data points, right? Then I got to come up here. My X's now need to go. I need 100 of them. That should put me at about 995 or something like that. Just short of 100, if I do this right. Okay, yep. My function values. Got to carry out 100 of them now. Okay. And the areas. We're going to have 100 areas now. So what happens is, as you have more rectangles, you get a better and better approximation to the area under the curve. We're still fighting that asymptote over there a little bit, but I think this will show you that our answer will start converging a little better. Now I know it looks like it's a little small, That's because the summation needs to be increased as well. And I think we were at, what, 5.09 before, if I remember right. And now 5.2. And, you know, I could run that to 500 points and get a little bit better, a little bit better, a little bit better. And again, there's better numerical algorithms for handling things like this. Another thing I could do is I could go back and apply the trapezoid rule or a little bit more fancy math. So, you know, my midpoint rule is a pretty good rule. Has a little trouble sometimes handling asymptotes. But again, notice that that was expected. I mean, my original picture here, I could see, there's quite a bit of green area here that's not really taken into account here. So I was expecting my answer to come in a little on the low side. I think I looked this up. It's 5.2 something. I'm at 5.2 sig figs, but I think the answer is very consistent with my expectations for the method. So, yeah, I think that's enough for now. We've beaten this problem to death, and I think I'll make some videos here showing numerical analysis with Excel for this class and for physics and my math classes too. So anyway, hope this helped. Everybody have a great day.